Hello everyone. Welcome back to the sessions on the advanced communication. Today it is the session 4, and in this particular session we are going to learn about the frequency limitations of the conventional tubes here. That is the frequency limitations of the conventional tubes. In this particular it is the interelectrode capacitance, lead inductance, transit time effect, gain bandwidth product limitation, RF losses. Now these are the some of the points we are going to cover in this particular session. Yes, already we have discussed in the introduction class of the microwave. That is, for the microwave signals, we cannot use the conventional electronic devices there, like the transistor and all, because they will cause some problems, because at the microwave frequency range those devices cannot operate properly there. Therefore, to overcome with those, for the microwave frequency only we are having the different devices there, special devices we need to operate at the microwave frequency range here. Now in this session we'll study what are the limitations, what were those problems which are causing by using those conventional devices here. First one is the interelectrode capacitance problem here. Now in this case, interelectrode capacitor problem, just observe here. Suppose this is one tube, it may be the transistor or tube here. Now it is having the anode, cathode and or the cathode plate and the gate here. This plate is also called as the anode, cathode and the gate. Now if you consider the basic of the semiconductor devices, that is basic of the semiconductor devices, if you consider, if any transistor, if you consider, it is made up of the 3 layers here. Correct? That is PNP or NPN. It is. This is P, N and P here. Or it may have the in other way. That is, if you consider one more NPN transistor, means it is again it will be the 3 layers here. This is N and this is P and again this is the N here. Correct? NPN or PNP here. Now what will happen if any two different types of the materials are joined, semiconductor materials are joined, there the depletion region will be generated in between. For example, if you consider here, the depletion region will be generated here as well as here the depletion region will be generated. And what all are there in the depletion region? If you consider the depletion region here, means here it will be having the fixed ions here or the fixed charges. For example, plus, and here it is minus, 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 minus. Correct? Like this depletion region is having these fixed ions here, positive ions and the negative ions here. Now what will happen if you consider this particular structure here? Now this will act as a capacitor here. Now this will act as a capacitor. Now what will happen whenever the particular device we will use at the lower frequency ranges, this won't come into picture. This won't come into picture. Why? Because X is equal to what? 1 divided by 2 pi Fc. X is equal to 1 divided by 2 pi Fc here. Therefore the capacitor is impedance and the frequency are inversely proportional here. Both are inversely proportional. Therefore, if frequency is less, means this Xc is very high. Impedance will be very high. If impedance is very high, means they will act as an open circuit here. They will act as actually physically we are not connected these capacitors, but that particular region will act as the capacitor here. The in between the connected region P and P, those depletion region is acting as a capacitor. At the lower frequency ranges, these won't come into picture. Why? Because if F is low, X is very high. X is very high means what will happen? That is, X is very high means it will be like the open circuit here. Correct? It will be like the open circuit. Therefore, it won't comes into picture only. It is like not connected only. Actually, physically also we are not connected. That effect is also not there. This effect is also not there. Therefore, the device will work properly here. But if you consider the at higher frequency ranges, if you consider for the at the higher frequency ranges, what will happen? If F is high means X is very low. X is very low. If X is low means it is like the short circuit here. If X is low means it is like the short circuit. Then short circuit means what will happen? For the short circuit it is, now it will be like shorted here. Correct? It is like shorted from the input to the output, like this. Input to the output means it is shorted. Now what will happen when this is shorted? Part of the output we are taking again back to the input here. Part of the output again we are taking back to the input. Therefore, it will be like the again negative feedback here. Part of the output again we are feeding to the input. Therefore, the ultimately the output will, what will happen to the output? Output will reduces there. Output will reduces. Therefore, the performance of the device is reduces. Now, for this reason, we cannot use these conventional devices at the microwave frequency, at the higher frequency range, because of this inter-electrode capacitance here. Because of this inter-electrode capacitance. Now, if you consider the particular lead inductance here. Now, in case of the lead inductance, if you observe here, the every lead here which we are connecting to these terminals, those are the wire leads here. For example, gate, plate, and the cathode are there, or the emitter base collector are there, anode, cathode, and the gate are there. To those terminals, whenever you want to feed some input or take output, we will make connection with the wires there. Okay. Now those wires and this lead, now what will happen? They will act as an inductor actually. Those wire or the leads are acting as the inductor here. Now this is also actually physically we are not connected inductor, but that particular part is acting as the inductor. Again, if the input is applied here to this point, whatever the input is applied, that should reach this point correctly without any attenuation. If it is short means here, then it will reach as it is. Then it will reach as it is. But actually, what will at the lower frequencies? Correct? At the lower frequencies, XL is equal to 2 pi FL. Means if F is low means what will happen? XL is also small here. XL is also small means it is like the short circuit. For the lower frequency it is the short circuit. Therefore, at the lower frequencies it will be like this. Whatever you apply that will be reaching here. But at the higher frequency what will happen? As the frequency will increase here, the XL also increases. If XL is more means it will be like the open circuit here. It will be like the open circuit, and whatever the input is applied here, that is unable to reach correctly at the other end. That is unable to reach correctly at the other end here. Therefore, this is also one of the major problem here. That will occurring only at the higher frequencies. Now, this is called as the lead inductance problem here. Lead inductance problem. Next one is the transit time here. Transit time effect. Transit time means what? The time taken by the electrons to travel from the cathode to the anode. Whatever that time duration is there, that is called as the transit time. For example, if you consider here, here is the cathode plate and here is the anode plate here. Okay. Now suppose electrons are generated here means immediately they will reach the from the cathode to the anode here. From cathode to the anode, for the frequency is less. If the lower frequencies, at the lower frequencies within no time they will reach here. At the lower frequencies, very short time they will take and they will reach from cathode to anode. But as the frequency increases, that is at the higher frequency here, what will happen? The time taken by the electrons to travel from this cathode to anode, it will goes on increasing because this transit time and the frequency are directly proportional here. If frequency is high means the transit time also increases there. Therefore, this is also one of the limitation or the drawback of using those conventional devices here. Okay, now say next one is that is transit time is the time taken by the electrons to travel from the cathode to the anode here. That is the time duration which is taken by the electrons to travel from the cathode to the anode is called as the transit time here. At low frequency, the transit time is finite and very negligible. Means it is very small value here. But at the higher frequencies, the transit time becomes an appreciable portion of a signal cycle, which results in the decrease in the efficiency of the device. As the time increases to reach the electrons from the cathode to the anode, it is taking more and more time as the frequency will increase. Therefore, that will ultimately going to reduce the efficiency of the device. That is also one of the major problem here. That is also one of the major problem. That is the transit time effect here. This is also one of the major problem in the higher frequencies. Now, the transit time depends on the cathode and the anode spacing and the static voltage between the anode and the cathode. That is, it depends on the spacing between the cathode plate and the anode plate, as well as the voltage between the anode and the cathode. Therefore, that will going to affect as well as the frequency that we are using. If it is a low frequency, means it is taking less time, but if it is a high frequency, means it is taking more time here. Now the gain bandwidth product limitation. In case of the gain bandwidth product is independent of frequency. Even though it is independent of frequency, for the given tube, higher gain can be only obtained at the expense of the micro, narrow or the bandwidth here. If the bandwidth is very small, then we can get the higher gain. The higher gain can be possible only if the bandwidth is narrow here. Now the skin effect here. Actually, what is this skin effect? That is, skin effect is the tendency of the alternating current to flow mostly near the outer surface of an electrical conductor such as a metal wire. The effect becomes more and more apparent as the frequency increases. That is, skin effect means what here? Suppose any metal wire or the conductor is there. Suppose this is one conductor here. We are passing current through the conductor here. Now when we are started passing the current from here to here, what will happen? The current will be more distributed only at the upper layers here, but at the depth layers, for example, this is the conductor here, correct? This is the conductor. Now to this conductor here, so the current will be distributed more and more only on the upper surface here, correct? Now here it is not into the depth here. Now the remaining portion, whatever the remaining portion is there, here it will start acting as a resistance here. Here it will start acting as the resistance here. Now this tendency of the AC current, which is most nearly means it is most nearly flowing to the outer surfaces. It is called as the skin effect here. This is called as what here? Skin effect, means it is flowing morely at the outer surfaces here. Mostly at the outer surfaces, that is called as the skin effect. And it will be more and more when the frequency will increases. If the frequency if we go on increasing still the higher frequencies, then what will happen? The skin effect will be more, means the more and more current will be only at the top layer. It is not distributing throughout the conductor. Therefore, that is also one of the major problem of this particular conventional devices using at the microwave frequency range here. Now, these are the some of the topics which we have discussed. That is, what are the limitations of the conventional devices at the microwave frequency range? In that, it is the inter-electrode capacitance, lead inductance, and the transit time, and the skin effect, and the gain bandwidth ratio here. Therefore, these are the limitations of the particular conventional devices. In the next class or in the next session, we will continue with the some of the microwave devices. Thank you.